So last time we talked about the three types of mathematical objects that are involved in the formalism of quantum mechanics. And this time around, I'd like to just review for myself the notion of vectors. And I'm going to go pretty fast through the basic stuff because I already know it. And I'm going to slow down for the things like dual spaces. And I'm going to be using Dirac notation through most of it. The Dirac notation is that weird bracket notation. So the first thing we need to look at is the notion of an abstract vector space. And that's a vector space over some field, usually over the complex numbers, for at least in quantum mechanics. And the properties that it displays or uses are that the vector addition is commutative and associative, and there is a zero vector for which x plus 0 equals x for all x in the vector space. And every vector has its own additive inverse. We call it negative x, I guess. And then also the scalar multiplication is associative, and that scalar multiplication is distributive over scalars and over vectors, and that the scalar 1 times a vector x gives you back the same vector. And of course, there's the closure properties of scalar multiplication and vector addition as well. Of course, one clear example of a vector space is that of the normal notion of arrows and the addition of those vectors by attaching them end to end, and then of scalar multiplication being stretching those arrows by the magnitude of the scalar. But there are plenty of other examples of vector spaces, and I just took a snapshot of what Wikipedia gives you, and there's functions confined over particular properties, and there are linear equations that can give you vector spaces, and so on and so forth. So you don't have to just rely on the notion of those abstract arrows. In fact, there are even infinite dimensional vector spaces, and I'll talk about dimension in a little bit. And some important notions of involving vectors is the notion of linear independence, which is when you have a collection of n vectors, if you can't express one as a linear combination of the others, no matter what, then you'd say the vectors are linearly independent. A more compact way is to say that the equation that I show here, the sum of a bunch of scalars multiplied by the vectors in the set, only has a trivial solution, meaning that the a sub i's are all 0. Another important notion is if a vector spans a vector space, that is defined as the case when every vector can be written as a linear combination of the n vectors that span the vector space. And if a set of linearly independent vectors V spans linear independent vectors in V spans V, then we call it a basis for V. And the number of vectors in that basis we call the dimension, or the number of dimensions of V. And so far we've covered all the algebraic aspects of vectors, and they're the abstraction of the usual naive arrow interpretation of vectors. But we're missing things like the length of a vector or the angle of the vector to another vector. And for this, what we do is we use something called an inner product between vectors. And it has the properties of having the inner product of W and V be the complex conjugate of the inner product of V and W. And in addition to that, we have what's called positive semi-definiteness, and that the inner product of V with itself is greater than or equal to 0, and only equal to 0 v is itself 0. And then we also have linearity of the inner product. What we call the square root of the inner product of v with itself is the norm or the magnitude, and there we have the analogy to the arrow notion of a vector. And then beyond that, we say that two vectors are orthogonal or perpendicular, if you want to go back to the arrow picture, if the inner product is 0. And we can also find the projection of a vector v onto another vector w by taking the inner product of w and v and dividing by the norm of w, which in the arrow notation would leave you with v cosine theta left. But then we wanted to point in the direction of w, so we multiply by the vector w. But the w itself might have a length, so we had to divide it again. So we have that w squared, the norm of w on the square of the norm of the w on the bottom of that. So and then if we have a basis for a space for where all the vectors are of norm 1 and they're pairwise orthogonal to each other, we call it an orthonormal basis. And this basis is rather important because it allows us to have certain representations that are convenient for use. Once we have an orthonormal basis, then any vector in the space of v can be written as a sum of projections of that vector v onto each vector on the orthonormal basis. We can call these projections components of the vector with respect to our particular orthonormal basis. And the thing about when we do this is that we can actually list each component as an entry in a column vector, which is basically a matrix with n rows and 1 column. And what's neat about this representation is that, again, when we have this orthonormal basis, we can express another vector in the same manner. And if what we do is take the transpose of it and take the complex conjugate, which basically just flips the Dirac notation, then our dot product just becomes multiplying the appropriate row matrix with the appropriate column matrix. And if you think about it a little bit more, we can generalize these row vectors as being one corresponding to having one row vector corresponding to each column vector. That is, you take the column vector, take the transpose, and take the complex conjugate of all the entries. Then we have its corresponding row vector. And if we do this for the whole vector space, then we'll have something we can call a dual space. Now, I wanted to go into the dual spaces a lot more in depth, but I wasn't able to look into it too much. I know that there's a lot more detail in terms of being linear functionals and all sorts of other stuff that if I wanted to do a rigorous study of it would warrant a lot more explanation and thought. But for right now, we'll just take it as being the conjugate transpose of the appropriate column vectors. And in Dirac notation, we call these column vectors kets, and these row vectors are bras, or that's the way I pronounce them. So that together you'll get this brac ket notation. And I think I'm going to stop there. Next time, hopefully, I'll cover operators and maybe eigenvalues. And then I probably need to do a section on infinite dimensional bases and things of that sort. But for right now, I think this is a good overview of what vectors are.